Hello everyone, welcome to the lecture series on Fundamentals of Generative AI and Large Language Models. We are in the week 3. In the previous session, we had seen the encoder part of VAE, Variational Autoencoder, and in this particular session, we will look into the decoder part of VAE. We will look into ELBO, which is called an evidence lower bound, and towards the end, we will connect it to the loss function of VAE. This is an important session because in this particular session, we will be covering some of the concepts which we have raised even in encoder part, and there were some questions which were not very clear in encoder. Those things will be answered here, and towards the end of this particular session you will get a complete idea of how the encoder works, how the decoder works. So, if you are listening to this particular session, I request you to see the previous session also once, and only then you will have a complete clarity of the overall working mechanism of the variational autoencoder. So, let us get started. This is what we have seen. The encoder is going to give us the output. What output the encoder is going to give? The mu and then the mean and then the variance of an approximate posterior distribution. This is what the encoder is going to give us the output. Right. From our previous session towards the end, when we have seen a numerical example, we had also seen how Z is sampled from this distribution. The theory says Z is sampled from a distribution. We have also seen one with the mathematical example that we had seen in our encoder part of VAE. So, once the encoder gives mean and variance of an approximate posterior distribution, the next thing is Z is sampled from this distribution. So, this also we have seen in the previous one. Z is sampled from this distribution. The meaning of sampled is randomly picking one number from this distribution. Now, we have Z. This is what is our previous part. Now, once we obtain Z, is it not Z is passed as an input to an decoder? So, we have the decoder now, where Z is passed as an input to an decoder. What is the role of a decoder? So, what is this VAE is all about? It is used to generate a new data or for a reconstruction, primarily for generating a new sample or new data. So, here decoder is to either give to generate or reconstruct the data from where? From this Z as an input to an decoder. Therefore, decoder is a neural network that takes Z as an input and then it gives us the output. What is that output? What is the role of a decoder? You remember this is a probabilistic model, which means we have a probabilistic encoder and then a probabilistic decoder. If that is the case, decoder also has to output the parameters, and those parameters are likelihood distribution. What is likelihood distribution? What is the probability that we get X given Z as an input? Right. So, decoder is a neural network that takes Z as an input and then outputs the likelihood parameters, parameters of likelihood distribution. Now, these parameters depends on what kind of data that you are going to reconstruct, whether you are going to reconstruct the continuous data or whether you are going to reconstruct the binary data. Depending on that, these types of parameters are going to vary. So, the types of parameters produced by the decoder mainly depends on the type of data being generated. So, the first possibility is it can be a continuous data. If it is a continuous data, then the output of a decoder is mean and variance. So, then X dash or the generated sample is sampled from this distribution. So, let me make it very clear. So, decoder has to output, give us the output. That output depends on the type of data that the decoder is reconstructing or the type of data the decoder is generating. If the decoder is reconstructing or generating continuous or real values, then the decoder is going to give us the output mean and variance. Okay, and theoretically we say that this x hat is being sampled from this distribution, is sampled from this distribution which is having mean and variance. Here decoder is being defined as what? Defined as Gaussian, right. So, what you have to remember here is, suppose if it is an real values or a continued values, then it is modeled as Gaussian, and decoder is going to give us the output mean and variance. And theoretically we say that x is sampled from this distribution, but practically whatever is the output, that is mean and variance, that is the reconstructed one. So, that we will see probably in the next session, where we are solving one entire problem. But now theoretically you understand this as, whenever we are going to get a continued require a continued values, then a decoder is going to output mean and variance. At the other side, what is done? What if we want a binary values? If it is a binary values, what is that the decoder has to output? The decoder has to output the probability for each of the feature or a pixel. What is the probability that each feature is either 0 or 1? So, which means it is a Bernoulli distribution. So, it is defined as Bernoulli distribution, and the x hat is sampled from this particular distribution. So, this is what is the decoder part. So, let us take one example, like how we had understood the encoder with one numerical example towards the end. Let us also understand decoder with one numerical example. That numerical example is this. Okay, let us understand this very carefully, so that the complete overall working mechanism of decoder will be answered in this particular slide only. Now, let us take this input. What is this input here? The input is original x, and here we have totally having 5 features. Therefore, we have 5 here. Okay. Now, once this is done, you will be passing it to an encoder. So, once you pass it to an encoder, what is that we have understood? Encoder is going to give us the output. What output it is going to give? It will give mean and variance. So, let us assume, since the latent space size is 2, here space size is 2, we are going to get 2 mean values and 2 variance values. Let us assume this is 2 mean and this is 2 variance values. So, let me erase it. Since the size here is 2, we are getting 2 mean and 2 variance. Even though if it is a log variance, convert it into a variance. So, it is 2 variance. Then what is that you are going to do? Since z is 2, we have z1, z2. So, z1 is sampled from where? From this and this distribution, and z2 is sampled from this and this distribution. So far we are clear. And we have seen in the previous session, what do you mean by sampling? Sampling is randomly picking one value. So, now whatever the value that randomly you pick, that will be this value. And z2, when it is sampled from this distribution, that is this value. Now, I will ask one question to the learners here. Whenever you sample one value, is that value fixed? What is your answer? The answer is no, the value is not fixed, right? If the value is not fixed, that means you will get one more possibility. This can be that one more possibility, and this is one more possibility for z2. Like this, how many such values are possible? Infinite. There is no end, right? Infinite such possible values. Are you understanding when I say infinite such possible? When I sample one value, I can get the value as 0.45, I will get 0.46, or I can get 0.55, 0.54, 0.51. There is no end when I sample a value. So, from this, when I pick randomly one value, probably first time I would have got this value, second time I will get this value, third time I will be getting this. So, there can be n number of such infinite such possible values. So, those are all these values. Is this point clear? let me pause and then tell you once again, because this is one important lecture where the entire VAE theoretically you will be understanding. We have taken an input x is passed to an encoder. The output of an encoder is mean and variance, right. Since the latent space is 2, we are having a 2 mean, 2 variance. Now Z1 is sampled from this distribution and Z2 is sampled from this distribution. Sampling here is randomly picking one number. When I say randomly picking one number, for a given input x, there can be infinite such Z1, Z2 and so on up to Zn, where n is an infinite value. You will have infinite such values. What do you mean by infinite such values? Probably initially it will be this and this will be 0.18. Then it can be 55, it can be 0.22. Then it can be 0.46 and this can be minus 0.02. It can be any. Like this, there can be n number of such values which are possible. For example, let us assume there are 3 samples where we have obtained 0.56 minus 0.11 as the first sample, which is Z1, and the second sample is Z2, which is 0.43 and minus 0.32. Third sample Z3 is 0.61 and minus 0.24. What do you mean by these? When you randomly pick the values from Z1 and Z2, this is the first sample, second sample and third sample. Are you convinced up till this point? Is this clear so far? I hope yes, answer is yes. Okay. Now, once you complete this, what is from our just previous slide, what did we understand? Once we get this Z, that is latent representation, we are passing it to a decoder. So, which means Z is passed now to a decoder, right. When Z is passed to a decoder, what is the decoder has to output? That depends on what kind of an input. Here input is this. If input is this, that is continuous value, what output it is going to give us is the mean and variance value, because it is defined as a Gaussian. Okay. Now, how is that a decoder works? When Z is passed to a decoder, decoder gives us x hat. Okay. So, is it not, this is the working mechanism of a decoder, pass Z and then we get x hat. Okay. Now, how many such Z's are there here? There are 3 such possible. Okay, just for an example I am telling you. So, now here for an example we have taken 3 such samples, Z1, Z2 and Z3. Now, Z1 when you pass it to an decoder, is it not, it is going to give us this, this value? Agree? Right. Now, I am just giving one example where Z is passed to an decoder and then decoder has to give us this x hat, and x hat, how many inputs are there? There are 5. So, definitely decoder also has to give 5 values. We have seen this from our encoder. Your architecture will be such that towards the end you will be having 5 5 neurons, and definitely you will be getting 5 such values. So, let us assume those 5 values are these. When you pass Z1, you got this. Now, there are 3 such different samples. So, when and you see this vector is different from this vector. Agree? Yes. Now, when you pass Z2 to a decoder, is it not you are going to get slightly different values? Let us assume those values are these. Now, when Z3 is passed as an input to an decoder, decoder has to give us the output. Let us assume the decoder has given us this output. Look at this very carefully. Let me clear the screen and then look into this. What is that we have done? We have taken the input and then we have obtained the latent space, and latent space has infinite such possible values for the given input. Agree? What do you mean by infinite such? Whatever we are seeing here. When you sample one value from that particular distribution, you will get infinite such values, which means there are infinite such samples. Now, every of Z when it is passed to an decoder Decoder has to give us the output. What output decoder is giving? Here, because the input is 5 features, decoder also has to give 5. Our architecture is such that the last layer is having 5 neurons. So 5 output we are getting. So when you pass Z1, is it not we got this output? When we pass Z2, is it not this? I am just giving as an example, just for an visualization, for an understanding. When we pass Z3 to a decoder, we are getting this. Now, when you look into all of these, what is one common we have? Is it not all of these features, the values that we have obtained, x1 hat, x2 hat and x3 hat, all these are very much closer to the original x? Can you see? There is a slight variation, but in and around it is playing around those features only. Why there is a variation? There is a variation because there is a variation in Z that we are passing to a decoder. When there is a small variation in the decoder input, definitely there is a small variation even in the output also. So, is it not, what is generative model? Generative model is, it has to generate a new data. Original data is this, and over a period of time, by the end of a decoder, after once the training everything is done, is it not we are getting a different output here? Definitely it is different from the original input. So far we were focusing on reconstructed, but what we are now focusing is generating a new sample. How is that we are generating a new sample? We are generating a new sample by learning the underlying distribution. Once that underlying distribution is learned properly, now you can ask where is that learning happened. So initially when the training is going on, probably the mean and variance will be very different values. Over a period of time, during back propagation, you would have updated those weights, and then over a period of time, whatever the values that we have obtained here will be the optimized values. With those optimized values, when you pass it to an decoder, definitely whatever the reconstructed or generated values will be very much closer to the original one. So did you get this concept? So here what exactly has happened? Input, for a given input, there are multiple such latent variables are possible, and there will be, since it is sampled from that distribution, each time you sample the values will be different. When the values are different, definitely that different values, see this is the first one, second and third, each time when you are getting a different samples, when you pass it to an decoder, decoder is going to give us the different output, but it is not, although it gives different, but it will be very much closer to the original input. That is what the reconstructed outputs are slightly different, because different latent vectors were sampled. However, all of them will remain similar to the original input. Now, this is what is the overall working mechanism of an decoder. Now, let us slowly one by one we will answer to all our previous questions. Now, see, do you agree to this? There are infinite many such possible Zs. Agree? Yes. You can keep sampling any number of times, and each time you sample the values will be different. So, infinite many such Zs are possible. Now, and for one observed, for a given input x, whatever the input that is given here, this corresponds to many possible latent variable representation z. Do you agree? The input what is given to us is this. For this input, you will be getting many such z's, and there are infinite such z's that are possible. So, this is what is being explained so far. Now, there is one question that we will be asking to ourselves. What is that question? Now, this is the input that is given, right? Now, for this, there are many such z's that are possible. So, many z's are there which are sampled from that distribution. Now, each z, when you pass it to decoder, you are getting some output. Now, there is one question. What is that question? For a given input, whatever is the training sample x, which latent representation z among so many z's, which z can produce or has produced this sample through the decoder. Which Z has given us the output? Can you tell one particular Z, this is the Z which has given us the output? No, we cannot tell. Why we cannot tell? Because it is just not one Z. You have multiple such Zs which are actually corresponding to we are getting that output. Now, if these are the different outputs that we have obtained, now I will ask the question, for this input whatever we have given, which Z has produced the output? What is your answer? Answer is no. It is not one such a Z, you have infinite such Zs, right. So, in order to answer to this particular question, now slowly we are connecting certain dots. In order to know which latent variable Z would have generated this observed input X or the given input X, if you want to know the answer for this, that can be calculated only by using the true posterior. According to the Bayes rule, this requires, in order to answer to this particular question, it requires computing this P of Z given X, right. Now, we know that P of Z given X can be computed using Bayes rule with this. Sometime back in our previous session, we have seen the denominator P of X is written in this way. Now, what is this? Now, this slide is very important. What exactly is this slide is all about is, now sometime back you had a question that, okay, you got the output. Now, which Z has given you this output? We cannot tell one particular Z has given because there are multiple such Zs are possible. In order to get that answer, you need to compute P of Z given X. To compute this, there is a problem that a denominator term is difficult. Why denominator term is difficult? The difficulty is actually here. This requires the integral, this is the integral where all possible latent variable Z that would have generated the observed. You have to consider all of those because it is just not one Z that has given you the output. There are multiple such Zs that has given you the output. So, you have to consider all of those. You have to take the summation of all of those. So, for a neural network, especially at a decoder side, this integral is actually difficult. It is intractable. A technical term that we will be using here is intractable, which is difficult. Because of this difficulty, we never use an P of Z given X, we always go for an approximation. Okay. So, I hope you are able to connect the dots. Now, if at all if you want to answer which Z has is responsible for whatever the output that we have got, we cannot answer that because there are many such Zs that are that would be possible for getting that reconstructed one. In order to answer, you have to consider all of those. How many you will consider? Is there any limit for it? No. Therefore, for a neural network decoder, this is difficult. Further, let us understand why it is. P of Z is an prior distribution which we know that we have assumed it to be a Gaussian. Gaussian is having these parameters. Okay. Now, slowly you see this. Every Z, that is the latent, in the previous slide if you go back, okay, if you look into this, there are many such Zs that are possible. Now, let us go back and then look into this particular question. For every possible Z, what is the decoder gives? What is the probability? Look into this. What is the probability that this Z could generate this X? Correct? Now, you have obtained some output. You from our previous slide, when Z is passed to an decoder, you have got some X hat. So, once you get this, the model is going to assign some probability, right? It can be 0.8, 0.2, 0.1. So, it is assigning some probability. So, for each of these Z, the decoder is going to assign the probability. What is the probability? What is the probability that you would have got this X from this Z, or this Z could generate the observed X? read in whatever, it is one and the same. It is going to assign the probability. Okay. Next, there is one more term. What is that one more term? You see this. What is this term? I am explaining why P of x is difficult. So, for every of z, decoder is going to assign one probability. What is that probability? Okay, if you have obtained, what is the probability that you obtained this x hat or x from this latent representation z? Okay, or this z would generate the observed x. What is the probability that this z would have generated that x? That is what is the first term. Now, what is this second term? Now, for each latent vector also there is some prior probability. What is the meaning of this? For each latent vector. Now, can we say this is one latent vector, this is one latent vector. For each of these latent vectors, this is one sample latent vector, this is one. For each of these latent vector, there is one probability that the model will assign. What is that probability? If the values which are there in this vector, if those values are very much closer to 0, which means they are very much closer to origin, then it is going to assign high probability, high prior density. Here Z1 is going to get, since it is very much closer to origin, it is going to get relatively high prior density. Okay. Now, since here the values are not very much closer to 0, then it is going to give a very low prior density, right. Now, which means here it is going to assign some value, here it is going to assign some value. What is the total contribution? Is it not the total contribution is the product of these two? Product of this and the product of this, right. The total contribution of each possible latent vector is this. And when you have to compute P of x, it is the integral, it is the sum of all such values. How many such values we have? Infinite. So, denominator is difficult term here. That is the reason we encoder never aims to learn P of z given x. Instead, encoder learns Q of z given x. Now, you can ask by using certain learnable parameters, fine. Now, you can ask, ma'am, what is the difference between this and this? Here also it is the probability, here also it is the probability. In what way these two are different? Look, this is actually an posterior, approximate posterior, which when you pass it to an neural network, it is just giving you the output mu and then the variance. Whereas, if your aim is to learn this, what is this? It is a base rule. What is base rule? Base rule says you should have this, you should have this and you should have this. Now, if you have this as your base rule, the denominator is very difficult because it requires the integral of infinite many such all possible latent variables z. So, there is no end for that denominator. That is the reason. Now, you can ask, is it not the problem in Q of z given x? No, the Q of z given x is not following this Bayesian rule. Q of z given x follows the Gaussian, where it will tell that I should only output mean and variance. But whereas P of z given x follows the Bayesian. If it follows the Bayesian, it has the denominator term. In the denominator term, you have that integral over all the possible latent variables. What do you mean by all possible latent variable? Now, if decoder has given reconstructed z, which is reconstructed output x, then which z is responsible for getting that output? It is not one such z, it is many such z's. If that is the case, you have to consider all of those. That is the reason encoder always follows approximate prior distribution, approximate posterior distribution, but not the true posterior. This is the answer for what was the question raised in our encoder part. This is the slide where you will get an answer. Most important slide where this is difficult to compute. Why? Because it has this term. What is this term? For every possible z, decoder gives what is the probability that this z would have generated this x. And the second, for every of the z, there is one prior density that we are assigning. How are we assigning? If that z has all the values closer to 0, which is closer to origin, then we will get the higher prior density. If the values are far from the origin, that is the values which are not 0, then we get the low prior density. Then for one z, what is the total contribution? The total contribution is this. Like that, many such z's are there. So it is the integral, which is the addition of all of those. That is the reason, instead of enforcing the encoder to learn this, we are enforcing the encoder to learn this part. Now, do not get confused, the difference is only P and here it is a Q. No, here it is a true posterior, P is a true posterior where it is following the base, whereas here it is forced to follow the Gaussian. Because of that, it is outputting, it is giving us the output mean and variance. I hope this is clear to you, one of the most important concept. Okay, let us proceed. Now, we are slowly moving towards the loss function. Now, what is the loss function in VAE? You remember we have prior distribution as Gaussian, then encoder Q of z given x is Gaussian, who is ensuring, then we used the term KL divergence. So, slowly let us move towards that. Now, suppose the training data has MNIST handwritten digit data set. If at all, if the model is very well trained, what is our ultimate outcome? What do you think are ultimate, what is that you are expecting from the model if the model is very well trained? If all those distributions are learned properly, reconstruction loss, everything is being learned properly, the training went very well. If that is the case, what is our ultimate expectation? If it is really an handwritten digit, the model should give higher probability to that particular sample. What do you mean by higher probability is, it should say confidently that the model, it is an handwritten one. The model should give high probability to, digit-like images. If there are some noisy, if it is not an handwritten one, if there is some disturbance for those images or the data, it should assign the lower probability. This is what we expect. Then only we say that the model has learned very well the underlying distribution. Do you agree to this? I will pause here and then I want you to think about what the statement I have made. After once the training is completed, what is that we are expecting from the model? Once the training is done, it means the model has learned the underlying distribution. If it has learned the underlying distribution, if it is an digit-like images, handwritten digit-like images, the model should give higher probability to it, or otherwise it should assign the lower probability, which means our aim is to maximize this. This is our aim. It has to maximize the log of p theta of x, it has to. But just some time back we have seen that computing this is very difficult because it has to check all possible latent variables that would have generated this x. So, it is very difficult, right? So, which means this is not our aim. What is our aim then? So, instead of directly maximizing log p theta of x, can we maximize some other objective? What is that other objective is? ELBO, which is evidence lower bound. So, instead of directly maximizing p theta of x, we are maximizing a simpler objective, and that objective is ELBO. Now, what is ELBO? Is computing the lower bound of p theta of x, log p theta of x. Therefore, instead of VAE, instead of maximizing log p theta of x, it maximizes the ELBO. VAE maximizes the ELBO. So, what is that we are understanding from this? Once the training is completed, once the model has learned properly, the aim here is for all correct samples it has to give higher probability, for all incorrect or for all noisy one it has to give the lower probability, which means our aim is to maximize this. If our aim is to maximize this, problem is it cannot be computed because of all possible latent variable z that would have generated x. So, therefore, we cannot keep this as our objective. Our objective should be maximize the ELBO. Now, let us understand what is ELBO. ELBO formula is this, where the first one is reconstruction. What is a reconstruction? How do you get this one? Is it not from Z you have sampled what is the role of an encoder? Encoder would have learnt this distribution. Once encoder has learnt this distribution, Z is sampled from this distribution, yes. Once Z is sampled from this distribution, that sampled value is given to an decoder. And what is the role of a decoder? Decoder has to give the maximum probability for that particular sample, right. So, if the decoder samples Z from this appropriate posterior, can the decoder reconstruct the original input x with high probability, which is nothing but an reconstruction, right. So, once again this in a very simple term I am explaining. Z is sampled, encoder has learnt mean and variance. Once mean and variance is learned properly, then once mean and variance is learned properly, then Z is sampled from that distribution. If Z is sampled from that distribution, when that Z is given to an decoder, decoder has to output us again mean and variance if it is a continued values. So, if this learning is proper, if encoder learning is proper, definitely reconstruction is proper. So, the first term here is a reconstruction term, and if it is an continued values, here in this particular place we will be using mean squared error. Suppose if it is an binary, in this particular reconstruction place we will use binary cross entropy. Is this part clear? You can take some time to analyze what is being explained, so that you are with me up till this point. I hope this is clear to you, right? Okay. What is the second term? Second term is KL divergence. From our previous session we have seen what is, from our first session in week 3, we have seen what is KL divergence. So, what is KL divergence here? One, you remember from our encoder session, prior P of Z is encoder, is Gaussian, I am sorry, P of Z is Gaussian. Then encoder has to learn some distribution. Instead of learning some complex, we have assumed again it to be Gaussian. So, there are two Gaussians. So, this KL divergence will ensure that both encoder distribution remain closer to a prior distribution P of Z. Okay. So, this is what is ELBO. ELBO is where you have an reconstruction and you have your KL divergence term. In this, the very first term that is reconstruction is called the log likelihood. In VAE laws, the first term is called log likelihood. And what is log likelihood? We always expect the model should give the higher probability for the observed data, which means our aim is maximum. But neural network, how it is being trained? Always it has to minimize the error. If it has to minimize the error, it cannot be maximum, it has to be minimum. How from maximum you will convert to minimum? Minus. Is it not? From max of some function, if you want to convert to minimum, it is minus, right? So, we convert max into minimum. That max is converted into minimum with minus. So, once again I am repeating, the first term is called log likelihood, and what is that we always expect? It has to assign higher probability for the observed data, which means maximum. The first value should be max of. But neural network is always trained to minimize. What is that? Not a maximization, minimize the loss. If it is a minimization, max function is converted into minimum with minus. Therefore, you see how the loss function is. The loss function now is the minimum of it. So, minus of this whole term, if you give minus first term, minus of minus becomes plus. So, this is what is the total loss function or the VAE loss function. Important slide once again. ELBO says reconstruction and then the regularization term, but first term is a maximum. We do not want maximum, we want to minimize, therefore max is converted into minimum. In the process of converting, the first term is getting negative term, minus of this is the positive value. Therefore, the VAE loss function, the first term is a reconstruction. If it is an continued value or real values, this first term becomes mean squared error. If it is a binary, the first term becomes binary cross entropy, right. And the second is KL divergence. What is KL divergence? KL divergence is represented in this form because the first is, this is Gaussian, which is written in this way. This is a Gaussian, which is written like this, right. Now, because these two are Gaussian, in a closed form, we are writing in this way. Why it is called closed form? So that you can substitute some values and get some number. So, in the closed form, this equation equivalent is whatever we have written here. So, in our previous session, we have already seen how this equation is derived. Okay. So, this is the closed form KL divergence. When both distributions are Gaussian, KL divergence has a closed form expression written in this way. This is all about the VAE, where we have started with encoder, and there was some questions which were still not answered. Then we moved to decoder. In the decoder, we have overall understood how the working mechanism. Then we started answering one by one why true posterior cannot be used. There is one drawback here, which is still not a complete VAE. There is one drawback here. What is the drawback? Can you tell how Z is sampled? Z is sampled from this distribution. This is what is the KL divergence, which encourages encoder distribution to remain closer to prior distribution. Fine. Now, how is Z sampled? Z is sampled from the distribution, right? Which distribution? This is what we have seen in both the examples. Z is sampled from this distribution, and each time when you sample it, you are getting a different values, right? Each time when you are getting a different value, is it not there is lot of randomness? When there is a randomness during back propagation, how is that you will back propagate through this one part so that you can update the weights? Randomness always breaks the gradient flows, right? So, if that is the case, how will you make the back propagation? Back propagation is impossible in this scenario, right? So, this is important concept once again. Since Z is sampled from this distribution, and since this distribution each time you sample you will be getting randomly a different value, there is a randomness operation. Randomness always breaks the gradient flow, which means we do not have one fixed formula to get that Z. Z is sampled from normal distribution or a Gaussian one. So, because Z is not having a proper formula, there is no way that you can back propagate it. So, which means architecture is still not complete architecture. So, this led to a question called reparameterization trick, which will be our point of discussion in our next session. In the next, we are going to discuss the reparameterization trick, and then we will see, if you look into the last two sessions, this session and the previous session, nowhere we have seen the architecture of VAE. Only I started explaining you what is encoder, what is latent space, what is decoder, but we have nowhere seen a solid architecture diagram, because after we complete the reparameterization trick, we will see what exactly is the architecture of VAE. So, with this we have come to this particular end of this particular session. Thank you.